Hello, everyone. The topic of today is Kirchhoff law or Kirchhoff law, as you like the way to pronounce his name. He's a German scientist, so we should pronounce it as Kirchhoff law, actually. Let's start with the lesson objectives. Objectives of this lesson to explain Kirchhoff law for current and Kirchhoff law for voltage, and apply both laws, the first and second law, or the current and voltage law, to the simple electric circuit, and solve the problems using the both formulas or the both techniques. Let's ask first, why do we need to study Kirchhoff law or Kirchhoff law? Actually, Kirchhoff law provides a very smart and intelligent way to do a circuit analysis using a simple technique. This tool is needed from every electrical engineer or anybody would like to study electronics in the future. Kirchhoff law will be so much helpful for him. Kirchhoff came up with two laws. The first law, or the current law, states that the sum of current entering a junction always equals to the sum of the current out of the junction or leaving a junction. Or in another word, that current is conserved at a junction. But first, let's ask, what is a junction? As we see that this black dot is a junction, and the junction definition is a point where at least three branches of circuit paths meet. Of course, here we have, this is one branch, two, three, four. So we have four branches. This one, two, three, four. Four branches are meeting, but even at least three branches, when we meet, it will be a junction. Of course, from junction to junction is a branch. So every path connected to junction together is called a branch. So according to this law, let's apply this law. In this case, we have I only is entering to the junction, and I1, I2, I3 are leaving the junction, which means that according to Kirchhoff's law, I equal to I1 plus I2 plus I3. It doesn't matter how many currents you have going into or out to the junction, they should be the same. If we will consider here a junction, and I will consider this I1, I2, I3 entering, I2 and I3, and another three currents are going out or leaving the junction, I4, I5, and I6. According to Kirchhoff law, I1 plus I2 plus I3 should be equals to I4 plus I5 plus I6. I think it's simple. Let's see how can we apply this law for the different circuits. Firstly, the simple series circuit. And if we have a look about this circuit, we can find that all the components are connected in circuit, and this provides a unique path for the electrons, this path. And the charge here is conserved in both sides of the junction, or in both sides of the barrier here, which is connected everything in series, and this is really obvious. Because current is the same at everywhere, so there is nothing or there is no issue about it. But just remember that the voltage here will be divides, and this circuit is called voltage divider. If we will go to more complicated circuit like this parallel circuit, of course we have here branches, so we will focus only on the junction here. So the current that is entering this junction, which is this 3 ampere, equal to the current will be divided because of the junction here and here. Of course, what decides how much current will pass in this branch or this branch? Of course, it depends on the resistors. Here we have a lower resistor, here we have higher resistors, so here will be more current. And this is simply just like water. When water coming to the land, the water will move faster in the lower land, which here lower resistance, and harder in the higher land, just like higher resistance. From here we can see that the current that is entering this junction, the 3 ampere, equals to 2 plus 1 ampere, of course, as it is measured by these 2 meters. Let's see a problem, or let's solve one problem to understand the concept more. And here we have a circuit that is consists of 3 loops or 3 branches. We have here, this is one loop, and we have here a junction. Current will be split here and here. Of course, we need to calculate A1, A3, and A2. Also here, there is a junction. Current will be split here and here. Let's first start with the A1, and A1 can be easily calculated from the concept that the current leaving a battery or a cell equals to the current entering to the cell. If we will consider the conventional current that is moving from here, it started by A1, and also it is ended up here by this 0.27 270 ampere. So we can easily conclude that A1 equals to 0.27 ampere, which is just equal to this amount of current, or 27 milliampere, 270 milliampere. Now we would like to calculate A3, but we have to calculate A2 first, since the sub-branch is coming as a priority. So we will focus on the A2 here. We can see that before this junction, we have 80. If we will draw this junction separately, so we can see that there is 80 milliampere entering into this junction. This is 80 milliampere, and it is divided into 2 branches here. One branch is 27 milliampere, and the other is unknown, which is A2. From here, we can calculate A2 easily. So we can say that the 80 milliampere equals to 27 plus A2. And if we subtract 27 from both sides, we will have A2 equals to, it's 80 minus 27, which is equals to 53 milliampere. Quite easy. Let's go to this loop and focusing on this junction. Of course, the current A1 that we already calculate is coming. If we will separately draw this junction, we have here 270 milliampere coming, and this 270 ampere is divided. Here we have A3, and here we have 80 milliampere. Of course, we couldn't calculate A2, or we couldn't involve A2 and A, because there is another junction here. So we cannot pass it from junction to junction. It is one branch, and we are talking about only this branch. So we have 270 milliampere equals to A3 plus 80. And here easily, if we subtract 80 from both sides, we will get A3, which is equals to 190 milliampere. Easy, straightforward, just focus on the junction. Current entered to the junction equals to the current leaving the junction. Now, let's go to the second law. Firstly, we will remove what we write. Remember, physics is not about memorizing information. Physics is about understanding the physical situation and use the right formula or the right description for the problem. The voltage law, or the second law, which stated that in any closed loop network, the total EMF is equal to the sum of the potential difference drop. And this could be easily explained from the simple circuit. If we have a simple circuit that has only one battery and a resistor, we can easily realize the fact that the voltage drop here equals to exactly the EMF and the battery, which is 1 volt. Okay, what about if we have multi cells in one battery? How we can calculate this? This is really a tricky part always examiners are using. If we have, for example, another battery, and this battery is pushing in the same direction, so there will be no problem. We will just add, so here 1.5, here 1.5, and here we will have voltage drop 3 volt. But the tricky part, what if the berry, the cells of the berry are not pushing in the same direction? So let's examine another example. Let's see. If we have, for example, 3 cells berry here, this is 1, this is 2, and this is 3. So 1, 2, and 3. How this will be connected? As we can see, that here we have 2 berries pushing opposite to each other, and the third is in one direction. So 2 will cancel each other, those will cancel each other, and only 1.5 will be calculated. So the voltage drop here will be only 1.5. So to take care of this, it is a little bit tricky when you're combining different cells in the same berry. Let's go back to Kirchhoff voltage law, and let's have more complicated example, just like this series a circuit. We have 2 berries, and these 2 berries are pushing in the same direction, so we will just add them, and the addition of them will equal to the voltage drop in these 2 resistors. So E1 plus E2 equals to V1 plus V2. Easy and straightforward. Let's apply this law to something more complicated, just like this parallel circuit. In the parallel circuit, it is much easier in my point of view, because the voltage across every loop is the same. So here we will consider every loop as independent series circuit. So we have here one loop, and from this one loop, the potential difference, total potential difference, of course, E1 plus E2 equals to, the total EMF equals to the total potential drop. So E1 plus E2 will equal to V1, V2. That's the first loop. If we will consider the second loop, which is also E1 plus E2 is the total EMF, in this case would be equal to V3 plus V4. That's the voltage drop in these 2 light bulbs. Straightforward, easily, but we need still to apply or solve one problem. So let's go to the next slide. Here we have a very nice problem. That's a circuit consists of as we see, 3 loops. And as I informed you, we need to deal with every loop as one independent series circuit. So the first loop here, and the second loop here, and the third loop here, we have 3 loops. We will start by the first loop, and then every loop we need to calculate the unknown. Of course, we have here numbers of unknowns, V1, V2, and V3 unknown, but just we first decide the physical situation and which formula or which law we need to apply. So we'll apply Kirchhoff's second law. In the first loop, let's draw it separately. We have the 24 EMF, and we have 2 volts, V1, and the 12 volts. So we have 2 volts, that's light bulb, and we have V1, which we need to calculate resistor, voltage across this resistor, and we have another light bulb, 12 volts. That's all for the first loop, and it will work as an independent series circuit. And we can say that the voltage drop is 2 volts plus V1 plus 12 volts. That's equals to 24, the total EMF. And if we add if we subtract 14 from both sides, we will have V1, which is equals to 10 volts. That's so easy. Let's apply the same concept for the second loop, which will have 24 to 8 V2 2 bulbs. It's a little bit tricky here. We need to notice that we have here 3 bulbs, and the 3 of them are identical, which means that they have the same resistance, as it's given that all the lambdas and resistors have the same resistance, which is quite easy, but just we need to take care and count how many bulbs we have. So in the second loop, let's draw the second loop. We have 24 volts, and we have 2 volts, the same, no change, and then 8-volt drop here, V2, and there is 2 bulbs. It's important. We don't know what is the voltage or what is the resistance, but we just know that it is equal. There is nothing else. If we need to calculate this missing, of course, here V2 is just the voltage across one bulb, but we have 2 bulbs and it will be entering into account. So we can write that 2 volt plus 8 volt plus 2 bulbs times, let's say, V2, because they are equal resistance, so the voltage drop across them will be equal, equals to 24. If we subtract 10 from both sides and divide it by 2, we will have V2, which equals to 14 divided by 2, 14 divided by 2, or 7 volts. So every light bulb will have 7 volts if we will measure the voltage across only one light bulb, so we will have only 7 volts. Now let's go to the third loop, which is the easier one. And the third loop, we have 24, 2, and V3 only. So the 24 volt will be dropped in 2 volt and V3, which means that V3 equals to 22 volt. This easily can be done. As you can see, we separate every loop and we calculate the total EMF in every loop and the voltage drop as we equal them together, which is the main technique of Kirchhoff. Let's have a look about some simulation. And of course, the simulation is very nice technique that we can use to represent a problem. I have 2 simulations. The first simulation for just a series circuit consists of 3 resistors and a battery. And of course, the main thing here is to calculate the current everywhere. The circuit, we call it a voltage divider because the voltage of this battery will be divided on the component. But because it is only one loop or only one path, we can use the ammeter to measure the current at different points. So here it's 0.45. If I measure the current somewhere else, for example here, if I measure the current here, I will find let's measure it here. Put it. It is 0.45. It is the same. Let's measure it in another location here, for example. Sometimes it's not accurate or there is a problem in the simulation, but the current should be everywhere the same. That's just about connection. So if we connect it like this, that's proof that the current is everywhere. It's the same as everywhere in the circuit, and this is proof of the Kirchhoff current law. If we will go to the other circuit, this is a parallel circuit consists of 3 resistors, so they are not equal. We can see that the current here It's different than the current here, different than current here, because the current divides for the branches, but the voltage is the same. So we measure the voltage here in this loop. It is 9 volts. If we will move the voltmeter branch to another branch, we will find it also 9 volts. If we will move it to the third branch, it is also 9 volts, which means the voltage is the same everywhere in the circuit, because it is back divider or voltage is constant in this circuit. I hope that you get or you understand the concept, and I wish also that I have more time to have more explanation. Thank you for your time. Physics is easy, remember always. Goodbye.